This is the last and final chapter of the subject, and I think it's again worth starting by backing off a little bit towards the end of last class. I think there may be parts of it which are maybe difficult for you to follow. So let me remind you what we were trying to do. We had learned that space-time is described by 4 coordinates, so that if you're following some particle or some event, you label it with 4 numbers, ct, x, y, and z, which I want you to let me combine into a single vector r. And they are written as x0, x1, x2, x3. Now I'm on 2 minds about x2 and x3. Sometimes I carry them around, sometimes I don't. x1 is just our familiar x, x2 is y, and x3 is z. It's possible to arrange all the motion to take place in the x direction, in which case y and z don't change when you go from one frame to the other, so I don't usually bother with that. But sometimes I put it back, because if you had only 2 components, x0 and x1, you might say, hey, the world is 2-dimensional. So I want to keep reminding you now we think of it in terms of 4 dimensions. So at least for that reason, sometimes I carry all the 3 components of position, sometimes only 1. But I'm sure you guys can figure out from the context which is which. So going back to the simpler situation of only x and time, the point of those coordinates is that if you went to a moving frame, x1 prime will be x1 minus beta x0 divided by the square root, and x0 prime will be x0 minus beta times x1 divided by that square root, where beta is v over c. Sometimes it's useful to introduce gamma, which is 1 minus u squared over c squared. Also, to prevent all confusion, u will be the velocity of your frame relative to mine. V will stand for the velocity of some particle that we are both studying. So let's reserve the symbol v for motion of actual particles, which is why we are there. We are all observers, but we're observing something. That something has a velocity that I will call v, and you will call w, and u is the speed relative to your frame and my frame. All right, so this is the notion of space-time, because space and time are getting mixed up when you go to a new frame of reference. But even in this world where nothing is sacred, the following combination is very important, which we denote as x dot x. There's a new dot product now in space-time. The new dot product will be the square of the time-like part minus the square of the space-like part. If you wanted to bring in all the components of space-time, then you can modify it to x naught squared minus r dot r. R dot r will be x squared plus y squared plus z squared. So you can use either notation. Whenever possible, I'll just keep 2, but you got to remember, this is why it's a 4-dimensional dot product. And this is the same for all people. So I can calculate it, you can calculate it. Our x naughts and x1 will differ, but it's the property of the Lorentz transformation that if I square this guy and subtract it from the square of this guy, on the right-hand side, some magical things will happen, and I'll get the same combination without the primes. That's like the length of the vector. And that's called the space-time interval. Let's call that s squared, the space-time interval. If you took 2 events, separated in space by delta x and separated in time by delta t, then we like to use the symbol delta s squared for the space-time interval. That's the same thing applied to the differences rather than to the coordinate themselves. And this is invariant. Invariant is a term mathematicians use for saying same for all people or unaffected by Lorentz transformation. It's the analog of how far you are from the origin in the old days when I took 2 frames, one which is the standard xy, other is a rotated xy. If you go to the rotated frame, the components x and y change, but how far you are from the origin or what's the length of the vector is the same for all people. More generally, the dot product of 2 vectors is invariant under rotations, and this is the new dot product. We use the symbol dot product, but I don't draw arrows, because if I don't draw any arrows and use capital letters, it means it's a 4 vector. That's the x vector. Then I said, let's try to reason by analogy and try to invent a momentum vector. How did we invent the momentum vector in the old days? We said, let the particle move a distance delta r, a vector delta r, in a time delta t, and I divide by delta t, and take some limit. But I know this is a vector because delta r is the difference in two vectors. That the particle is now and where it is later, difference of two vectors is also a tiny vector going from here to there. Dividing by a scalar I mean something that is not affected by rotations, means taking a vector and multiplying it by some number. Therefore, that's also a vector. So this ratio is also a vector, and the limit of this ratio is also a vector. I'm sorry, I forgot the mass here, and we call it the momentum vector. So you can manufacture vectors starting with a position vector by taking derivatives with respect to something like time that is the same for all observers. Where observers, I meant in the old days, people with an axis rotated any way you like. I want to do the same thing now in this present problem, but I now want to define, obviously, a four-dimensional vector. So to do the four-dimensional vector, my plan is to define something called momentum, which is now going to be the change in this fourth position divided by something. Question is, what do I divide it by? I cannot divide by delta t. In the old days, delta t was a sacred number, same for all people. Now delta t is like delta x or delta y. It's one of the components, and you don't divide the change in the vector components by the change in one of the components to get a velocity. You got to divide by something that's going to play the role of time and have the same value for all people. Well, we sort of know what that quantity is. Obviously, if a particle is moving from here to here in space-time, this is x0 equal to ct, and this is x1. It moves the distance delta x1 in a time delta t. And we know that for this piece of its motion, the following quantity, delta s, which is c delta t squared minus delta x squared, is the same for all people. So I should really be dividing by this. Let me write it slightly differently. A c delta t times square root of 1 minus delta x over delta t squared times 1 over c squared. So we are asked to divide by this crazy thing. Well, let me write this crazy thing as c times something I want to call d tau. D tau is dt times square root of 1 minus delta x over delta t squared times 1 over c squared. Then I said, we can give a meaning to this thing. In fact, let's take derivative with respect to tau, not s. They differ only by this factor c, which is a constant, so it doesn't matter. Tau has units of time, and you can ask, what does that time stand for? It's not the time according to me, but I argue that it's the time according to the particle. Why? Because you can evaluate this quantity in any frame you like. So go to the frame moving with the particle. If you're moving with the particle, and if you're here now and there later, later is certainly later, but here remains here for the particle. It doesn't move in its own frame. So delta x will vanish. Therefore, delta s simply reduces to c times the time elapsed according to the particle. So d tau is the time elapsed according to the particle itself. According to particle. That's what we're going to divide by. So it's a very clever way to circumvent the question of what shall I take derivative with respect to. My time and your time all are variable. We don't agree on it. But let's ask how much time elapsed according to the one thing we are studying. Let's divide by that time. That answer will be the same because you and I may not agree on how long it took to go from here to there, but we can all ask how long did the particle say it took to go from here to there. We're talking about the same thing, and we'll get the same answer. To get the particle time, you've got to take the time according to you and me and multiply by this factor. This factor, by the way, is nothing but usual time dilatation. Because if the particle says it took time d tau, because the clock is slower by exactly this amount, I will say it took longer by this amount. So let's rewrite this in a way that's going to be more helpful to us. Take the ratio and write dt over d tau is 1 over square root of 1 minus b squared over c squared. I'm going to use that in a minute. That just says the time according to me and the time according to the particle are related by the time dilatation factor that's controlled by the velocity of the particle. Now we are ready to define the force momentum P. The force momentum P is going to be m times dx naught d tau times m dx1 d tau. I'm not going to bother with the other components. We can always put them back. Well, x naught, you remember, was ct. So this really becomes m dt divided by d tau times m dx divided by d tau. This is guaranteed to be a 4-vector. That means if you know the components of this in one frame of reference, and you call one of them as P0, and you call this one as P1, then in a frame that's moving relative to you at speed u, P0 prime will be P0 minus beta times P1 over the square root, and P1 prime will be P1 minus beta times P0 over the square root. It'll transform just like the components of x. Yes?
For P0, where did the C go?
Where did the C? No, it did not go. You're quite right. It is C. X naught is CT. You're quite right. It is C times dt. You need that, then this is correct. So we got a 4-vector, but we don't know what it means. Because we don't know what d tau means. It's, of course, it's the time according to the particle, but I don't care about particle. I'm studying this particle. I got my own clock. I got my own meter sticks. I want to think in terms of time according to me, period. Well, we can do that. We can do that by going to anything where you take a derivative, such as dx1 d tau, and you can write it as dx1 dt times dt d tau. dx1 dt is something we understand. It's just the velocity according to you and me. If you use that rule here, you will find the momentum has got components m times c. dt d tau is dt dt, which is 1, times dt divided by d tau, which is this factor here. And the second thing will be mv divided by the same thing. In other words, you can trade tau derivatives for t derivatives everywhere, provided you attach this factor. That's the ratio of the tau derivative to the t derivative. So now I have a 4-vector. I still don't know what it means, but at least it is written in terms of things which have direct operational significance for me. I see a particle moving. It's got a velocity. Put that in, and I get this thing. Apparently, the relativity theory says this should play the role of momentum, but a 4-dimensional momentum in your new world. If you want to bring the other components, we will put an arrow. We can keep it or leave it. Doesn't matter. Now, notice once again that, okay, I'll continue some more. I've already done this last time, but let me remind you. We looked at this guy and said, look, at small velocities, when v over c is very small, the denominator is just 1. Numerator is mv. Then I said, that's the momentum. So it must be that with all these factors, this is the momentum in the new relativistic theory. The new relativistic theory, momentum is not just mass times velocity. Mass times velocity divided by all this stuff. The theory says, use that as your momentum. That's good. Then we say, okay, that's my momentum. Who is this? I expanded this out for small velocity. If you put velocity equal to 0, you get mc. That looks like just the mass, and we don't know what that corresponds to. It's just the mass, nothing kinematical. But if you expand the square root a little further out to one more term, we found that the 0th component, P0, looks like mc times 1 plus b squared over 2c squared plus dot dot dot. That becomes mc plus 1/2 mv squared times 1 over c plus dot, dot, dot. And now I finally have something I understand, because 1/2 mv squared is familiar kinetic energy. But I don't like this annoying c here. If I multiply both sides by c, I learn that c times p0 is mc squared plus 1/2 mv squared plus more stuff that's more and more powers of v over c. But this, I argue, since that's the kinetic energy, everything is an energy formula, so the whole thing stands for energy. So I learned that the first component of P is energy divided by C. So I come back here and I write this as energy divided by C. So for all of you, or for many of you who found some of this mathematics difficult to follow, it depends. For me, it was love at first sight. This is really when I said I want to go into the business. For some reason, this worked for me. But it doesn't matter. What you have to know is what I'm going to tell you now. Operationally, I'm not going to hold you responsible for this part of the material at all. For me, it's part of explaining how logically, starting with the very first axiom, first two axioms, you can deduce everything. But now I'll tell you operationally what you guys are supposed to know. You are supposed to learn the following two things. In the old days, we had time and we had space. They have been united into a single quantity, CT R, which we write as x0, x1, etc. In other words, the three components of a vector joined with one quantity that look like a scalar together to form a four-dimensional object. Now we are learning that there's another four-dimensional object, one of which is just the momentum, and the other is energy divided by c. And we want to call that as P0, P1, etc. Again, the familiar momentum, which is a vector, joined with another quantity, which the best way to think about it is kinetic energy plus rest energy plus other corrections. But it's a scalar. It doesn't depend on orientation of axis in the old days. But now, under Lorentz transformation, namely when you go from one frame to another, E and P will all mix with each other, just like X and T will mix with each other. But this is the new four vector. This is called the energy momentum four vector. Just like that's called the space-time four vector, this is the energy momentum four vector. So all over relativity, you will find three objects, which is to be part of a vector, will combine with the fourth one, which used to be a scalar. Together, they will form a new four-dimensional vector. So we should know the following. When we are studying particle dynamics, we have to know in more detail. In fact, let me dedicate a whole board to that. It's very important. The new definition is that it's E over C and P. Yep.
I'm kind of confused how you know that that's energy. Just because it looks like energy?
Well, it looks like mc squared plus 1/2 mv squared plus other stuff, right? So I recognize 1/2 mv squared as an energy. Then the other powers involving v to the fourth, c to the fourth, they're all corrections, obviously, to the energy at higher velocities. Just like momentum, even in relativistic theory, was not mv. It started out like mv. But when you expand the denominators and powers of v over c, you'll get more and more corrections. I identify this as an energy. Because if I go to very low velocities, it reduces to the rest mass, which is never going to change, plus a 1/2 mv squared, which played the role of kinetic energy. Right? That's why it has units of energy, and one term in it looks like energy. So the whole thing, the theory is telling you, is all just the energy of the particle. In the old days, when velocities are very small, we saw only the two terms are written, 1/2 mv squared and mc squared. Mc squared, we didn't bother with because it doesn't change in any collision. You add the mc squares before, each particle has got its own mc squared. Before and after, they simply cancel. It's the 1/2 mv squares before and after that were equal, and we use that to solve collisions. Now we will be told you should use the conservation of this energy and the conservation of this momentum in a collision. Okay, so the first thing is, this is E and this is P, and anyone says, what is E? It is mc squared divided by 1 minus v squared over c squared, and P in one dimension is mv divided by 1 minus v squared over c squared. This you must know. So momentum in relativity looks a bit like the old momentum, but it's got this ubiquitous factor. And energy looks really weird, doesn't look like anything on Earth, but if you expand this in powers of V, you will see the terms we wrote down. Rest energy plus everything else you can call energy of motion. And the first term in the energy of motion is the familiar 1/2 mv squared. In other words, this is how the world always was. It was revealed to us in the old days when we only looked at low energy particles as mc squared plus 1/2 mv squared, and we couldn't see the ... terms because v over c was so small. The 4th power and 6th power and 8th power v over c were too small for us to detect. Likewise, the momentum of a particle was never mv. It was mv divided by all this. But for small values of v over c, it looked like that, and we figured, hey, that's what is really happening. So we were looking at an approximation to these quantities in the old days when velocities were small, and as velocities go up, those quantities are not useful. This is what the theory says should play the role of the new 4 momentum. So the significance of this being a 4 momentum, first of all, is what is written in the top right corner there. Namely, if you know the energy and momentum in one frame, you can find the energy and momentum in another frame of reference, moving relative to me. For that purpose, you should take the energy and divide by c. You should call it p0. The momentum can be left as it is, and this will behave like x0. That will behave like x1 under Lorentz transformation. But there are other consequences of the fact that p is a 4 vector. First consequence is this. You remember the dot product of a vector with itself is the same for all observers. So what's the dot product of p with itself? Well, before I do that, let me remind you in general, in relativity, you will have 4 vectors. A, they'll have one part that looks like time and one part that looks like an ordinary vector. And B is another 4 vector. It's got a part that looks like time and another part that looks like an ordinary vector. It's a union of a former vector with a former scalar. And they will transform under Lorentz transformation just like x0 and t. But the following quantity, a dot b, which is a0, b0, minus the usual dot product of the spatial components, is invariant. That means all people will agree on this quantity. And a special case is a dot a. A dot a is equal to a0 squared minus the length of the vector part, which for our purpose will be just a0 squared minus a1 squared. This is all reasoning by analogy. Yep?
Are these 4 vectors also what are called quaternions?
No. These are quaternions, are a slightly different object. You can form with these 4 numbers something that you might call a quaternion. Right. They were invented before relativity by Hamilton, and they have a great mathematical beauty, and they are generalization of numbers. You know, we generalize real numbers to complex numbers. Then we went from complex numbers to things called quaternions. They are also numbers. You can multiply them by each other, but the product AB differs from the product BA. So they are called hypercomplex numbers where the order in which you multiply them matters. Okay, so now let's ask what is the invariant length square of the momentum 4 vector with itself. That means you got to do p0 square minus p square. That means you're trying to take m0, you're going to take mc over this factor squared minus mv over this factor squared. Well, let's try to do this in our head, guys. M squared is going to come out of the whole thing, you agree? In the top I have got 1 over 1 minus v squared over c squared. Here I have minus v squared over 1 minus v squared over c squared. So they will all cancel, giving you mc squared. M squared c squared. So the 4 vector of any particle has a length that does not at all depend on how fast it's moving. It depends only on this. When you take a velocity vector for a particle, it doesn't have a fixed length. Particle can be moving slow, it can be moving fast. So Vx squared plus Vy squared could be whatever you like, depending on how it's moving. But this relativistic length square of a 4 vector is independent of the velocity, because the velocity here, when combined with this term, just cancels out. Well, that's just the way it is. Now, if you're not good in algebra, that's a shortcut for finding this. Let me tell you what the shortcut is. And we love the shortcuts because they're very helpful. And the moral of the story is also illustrated by the shortcut. I want to find P dot P. It's an invariant because it's like a dot product. So anybody can calculate it. How about somebody riding with the particle? If you're riding with the particle, your zeroth component is m0c, is mc, there is no velocity for you, and you have no momentum. As the particle has no momentum, as seen by the particle, so the components of the vector p become mc and 0. What's the length square of this vector? Well, it's the square of this guy, and k is closed. There's nothing here to subtract from here. So that's a quick way to verify that this length of the vector with itself is in fact m squared c squared. In other words, the trick is ride with the particle and calculate the vector. Then the vector has only one component, namely mc, doesn't have a spatial part because it's not moving according to itself. That's why P dot P is m squared c squared. So people write it also as follows. Remember, P0 was E over C. This is just P squared is m squared c squared. Now don't write it. This is one way to write it explicitly. But here is how people write it. Multiply both sides by c squared and write E squared is equal to c squared p squared plus m squared c to the fourth. That deserves a box. That's how we remember it. I have just rearranged this equation. P dot P is m squared c squared. By definition, P dot P is the time-like component square minus the spatial component square. We agree the time-like part is E over c. Spatial part is just the momentum. So I've just rearranged it to get this. And it says the energy of the particle depends on its momentum. If it comes completely to rest, you kill this term. That's E equal to mc squared. That's the rest energy of a particle. Now, I'm almost finished with the kinematics except for one thing. There are strange particles in the world called photons. A photon has no rest mass. Therefore, if you naively went by any of these formulas, if you kill the mass of the photon, you might think energy and momentum vanish because m is going to 0. But we all know enough mathematics to know that if it's 0 on the top, you could beat it if there's a 0 in the bottom. That will occur only for v equal to c. So particles moving at the speed of light do have energy and momentum, but they don't come from a mass divided by something, or mass times velocity divided by something. They simply have energy and momentum that obeys this equation without an m on the right-hand side. For a photon, E squared equal to c times p squared is what a photon obeys. So photons can have energy, and photons can have momentum, but their energy will be c times their momentum. So that if you find the invariant square of the photon momentum, you will get 0. So photons are particles whose momentum square is 0, where the square is the four-dimensional square with the time square minus the spatial square. So let me summarize once more for people who may not want to follow every detail. The practical part of what you must understand from what I've been teaching you is that when you study a single material particle which has a mass so that it can be brought to rest and made to sit on the table, we associate with that a 4 vector. The first part of that is the energy over c. The second part of that is called the momentum. And the explicit formula for these are m0 or mc divided by this and mv divided by this. And one can explicitly verify that P dot P is m squared c squared. This is it. This is a summary of all that I've said. If you don't know anything at all, know this. Yes?
When you're writing P dot P there on the right, that's the P that is the component of the 4 vector
Yeah, capital P without any arrows on it is supposed to be a 4 vector, and the dot product of it is defined as the square of the first component minus the square of the second one. That's correct. And for photons, we always like to use the symbol K for the momentum of a photon rather than P. Luckily, people agreed, more or less by convention. Photon momentum is called K, most sometimes, and it's called Q by some people, but we will call it K. And the energy of the photon is going to be called omega. The momentum of the photon is going to be called K. And the condition is omega equal to Kc. And that's the condition K dot K equal to 0. K squared, if you like, shorthand for K dot K, is 0 for photons. Photons are particles whose square of the 4 momentum is 0. Material particles that can come to rest have a square of the 4 momentum, which is m squared c squared. This is something you have to know. Another thing you have to know is that when I write them in this notation as 4 vectors, you should know the following. If I know the components, P0 and P1 in one frame, and you move relative to me at speed u, P0 prime and P1 prime will be related to P0 and P1 by the Lorentz transformation, just like x0 prime and x1 prime are related to x1 and x by that formula on the top left. Last thing I want to say, I'm going to do a lot of problems for you so you get used to doing relativistic kinematics. Last thing I want to tell you is, why do we take this definition of momentum? Okay, you agree the theory naturally gave out something that it said deserves to be called momentum, but what's so nice about this? Why is it important that the momentum and energy form a vector? I'm going to give you a reason for it and try to follow the reason. The whole advantage of energy and momentum, what is the big deal about energy and momentum? Let me ask you that. Yes? They're conserved. They were not useful unless their special utility came from the fact they're conserved. So you can put a restriction on possible collisions. You add the momentum before, it's got to agree with momentum after. You add the energy before, it's got to agree with the energy after. Of course, in relativity, energy and momentum have been assembled into 4 vectors. So conservation of momentum will mean really 4 equations. The 0th part will be the energy before will be the energy after, and the 3 spatial parts will be x component of momentum before will be x component after, and so on. That's all very good, but you got to make sure that if a momentum is conserved for me, 4 momentum, it must also be conserved for you. There's no use having a quantity that's conserved for me and not conserved for you. So by the time you bring up something and say we're going to use it as a conserved quantity, you got to make sure the conservation law is not limited to one observer. And that's what I want to show you. I want to argue without writing any equations that if energy and momentum are conserved for me, they're going to be conserved for you because they are vectors. Let's understand why. Suppose you got a collision, a lot of particles come in. One particle brings momentum, energy P1, other one brings out energy and momentum P2. And at the end of the collision, maybe they become particle 3 and particle 4 and particle 5. In relativistic theories, if 2 particles come in, you can have 36 particles coming out. In fact, that's why they build accelerators. If 2 went in and 2 came out, it's a waste of time. You can smash any 2 things, and with that energy, you can produce matter. So it's not a mistake I've made. I do mean that sometimes 2 can go into 3 or 4 or 5. Let's take an example where this is true. Each P is a 4-component object like this. Suppose I say incoming equals outgoing. Now, if you see the whole collision from your frame of reference, then I maintain that the numbers you get, P1 prime and P2 prime, will also equal P3 prime plus P4 prime plus P5 prime. That's guaranteed, and I want to tell you why. Suppose these were ordinary vectors, and let me make life simple by saying P1 plus P2 became P3. What that means is one vector P1, another vector P2, added up to one vector P3, except these are not ordinary arrows, these are arrows in 4 dimensions. The fact that 2 arrows add up to a third one, or equal to a third one, means they form a triangle. Now they can form a triangle for me, and you can stand on your head and do what you like. It'll still be true, even though it looks like this. It is still true that this guy plus this guy is equal to that guy. If two vectors add up to a third one, namely, if a sum of two vectors is equal to another vector, namely, the left-hand side vector is equal to right-hand side vector, going to a rotated frame will continue to say that the rotated vector is equal to rotated vector. That's because equal vectors upon rotation will remain equal vectors. That's the whole point. The total incoming momentum 4 vector, call it P incoming, and this is the outgoing momentum, call it the P outgoing. If P incoming is equal to P outgoing for me, so two vectors are equal in space-time, for a rotated observer, they will be equal. Do you understand why? Because my total incoming vector will undergo a Lorentz transformation to become your incoming vector. My outgoing vector will go a Lorentz transformation to find your outgoing. But if the input to the Lorentz transformation is the same, the output will also be the same, because you will be putting the very same numbers to get out the output numbers. That's why it's very important that this momentum that we have be used, because it has a chance that if it's conserved in one frame, it's conserved in all frames. If you went and said, you know what, I don't like your formulas, I am really wedded to this formula for momentum, what you will find is that even if it's conserved in your frame of reference, in a different frame of reference, that combination, sum over mv, would not be conserved. Okay, that's the final property of 4 vectors you got to use. Again, if you don't follow the details, you must know that in collisions that we are going to study, we'll add up all the 4 vectors coming in, we'll equate them to all the 4 vectors going out. That's it. So now I'm going to do sample problems to get you a feeling for that. So as usual, they will start out with the simplest one and then try to make it more complicated. So the first problem is this. I'm standing here, I got some mass m, and a photon is coming towards me with some momentum p. And it just hits me on the face and I absorb the photon. It's completely possible for the atoms forming my body to absorb a photon. They absorb it. So in the end, there is no photon, that is me, but possibly with a new mass, m prime. In relativistic collisions, there is nothing called inelastic collisions. Remember in the old days, if one thing came and stuck to another thing and they moved together, momentum is conserved but energy is not. There is no such thing. Energy will always be conserved in relativistic theories. In other words, even though this has become a single unit, you might say, what happened to the energy? Previously I had a moving photon, I got nothing moving here. Well, first of all, I will be moving. Secondly, I will have more mass. Best thing is to consider two particles coming in opposite directions. They collide and form a new mass. In relativity, there is no momentum in the final particle. It's not moving at all. But it will be more massive than before, and that extra mass times c squared will be the extra energy brought by the particles that formed it. So anyway, the question here is, what is m prime? That's what we have to figure out. So the equation we will use is, I will call my momentum as p, and I will call P1 as the initial one and P2 as the final one. Let's write down all the equations we can. The only equation in town is K plus P1 equals P2. K is now, everybody is a 4 vector, so don't be fooled. It's 4 equations. But in this problem, luckily, since there is no motion perpendicular to the x-axis, we can have just x momentum. There's no need for y and z, because the photon comes this way, it can knock me and I can start moving this way, but all the action is in the x direction. So here it will be actually 2-dimensional vectors and not 4. There's nothing vertically before or after. It will be 0 equal to 0. So what are those equations? Before you do that, let's write down the momentum of the photon first. Momentum of the photon has got some energy, omega over c, and it's got some momentum k, where omega equals kc. You got to remember that. P1 has got an energy which is mc and no spatial momentum because I'm not moving. At the end of the day, P2, I am moving, but I also have a new mass. And I have a new velocity, which we don't know. Then I have m prime v divided by square root of 1 minus v squared over c squared. Now, all of you should be able to write this part down. If you're not, you should take a minute, you should think about it, you can stop me, you can question me. But if you cannot do this, you cannot do any of the problems. So you've got to think, would I have done this? Does it make sense to me? What's the bookkeeping is all in the top. When you got a material particle, its first term, zeroth component, will be m times c divided by the square root of all those things. But if the particle is at rest, you only have mc. There is no momentum. The final object, me, after I got hit by the photon, I am recoiling. So I will have a velocity. I don't know what it is. But my energy in terms of that, the first term, P0 will be this will be P1. Now the law of conservation of energy and momentum, namely K1 plus P1 equals K2 plus P2, will really be saying all the energy parts, or the zeroth components, will add up before and after. And the first components will add up before and after. In other words, omega over c plus mc will be equal to m prime c over this. Then k plus 0 will be equal to m prime v divided by this. This is not any different from the old days. You had law of conservation of momentum, you have law of conservation of energy, except energy is not 1/2 mv squared. Energy is this crazy thing. Plus, even if a particle is not moving, don't forget to give it mc as the energy. That's the new part. So what is the question I asked you? I said, what is m prime? So your job is to take these two simultaneous equations, this one and this one, and solve for m prime. So what should I do? Can you think of a strategy that will give me m prime? Yes?
You said k equals the right side of that equation.
Yeah.
To the first one?
Into this one here?
Yeah.
Yeah. You still have to solve for m prime, and you also don't know the velocity here. Remember, you have to solve for the velocity, and you have to solve for the m prime. If you say, what is the unknowns and what are the knowns, let's be very clear. The photon has a known momentum and known energy that's given to you. Initial me has a mass m that's given to you. Your job is to find the unknown mass m prime and the unknown velocity. Two equations for two unknowns, but they're not simple linear equations where you can add and subtract. Okay, the simple linear equations are multiply this by 3, multiply that by 4, and subtract, and you'll get what you want. It's more complicated. The trick that you really want to use is the fact that for any particle, if you took the square of the zeroth component, subtract from it the square of the spatial component, the answer will be m prime square c square. So I'm saying this square minus this square will be m prime times c square, and that you get by taking the square of this minus the square of this. You can juggle that, but I'm not going to do it that way. I'm going to show you a much more efficient and rapid way to do this. So let's do it the more efficient way. So let me come down here so you can see. Here is the shortcut. Shortcut is to work entirely with 4 vectors and with 4-dimensional dot products, and don't get down to the ugly business of writing each component. We know that P2 is P1 plus K, right? And who are we after? We are after m prime. Then we remember that P2 squared, namely P2 dot P2, is equal to m prime square c square. Yes? So the question you're asked is, no one asked you how fast I am moving after I got hit by the photon. You're only asking me, what is my new rest mass? See, I've swallowed a photon, so I weigh more. It's really that. How much more do I weigh is the question, namely, what is my rest mass? Namely, I swallowed it, and I recoiled, and if you travel with me and find me at rest, what mass m prime will you measure? So no one's asking me, my velocity of recoil v. So you shouldn't bother to calculate that. You could if you wanted to, but no one's asking you that. So go directly for P2 square. So the quantity we're looking for is m prime square c square. That's got to be P1 plus k, the whole thing square. Well, do the old algebra. That's equal to P1 square plus k square plus twice P1 dot k. Okay, now let's see if I can do what we do next. Would you like to guess? Yes. No? Do you know any of these quantities? Do we know anything about what I've, of the three terms I've written here? Yes? K squared is 0 because of what? For a photon, I told, for any particle, the square of its momentum is really the square of its mass times c squared. For photons, I told you long back, k dot k is 0. You don't have to worry about that. How about the square of the momentum of me? Well, that was my rest mass before, times c squared, plus 0. Now, P1 dot k, you got to be careful. That dot product means, let me write down the vector P1 and k for you. P1 was mc and 0, and k was omega over c, and the spatial momentum where omega was equal to kc. Got to remember that. For a photon, once you pick the energy, you have no choice with the momentum. The magnitude of momentum has to be magnitude of energy divided by c. So let's take P dot k. Let's try to do P1 dot k. Remember, dot product of two vectors is time times time. M c times omega over c minus space dot space, that was 0. So I cancel that, and I find it's really m omega. And that's equal to m prime c squared. Yep.
Could you just remind me what the omega stands for again?
Yeah, the photon, remember the four vectors, first component is energy over c. Second component is the momentum. It's traditional to call the energy of the photon by the symbol omega. And it's traditional to call the momentum of the photon, the usual momentum, by the symbol k. And that's very helpful. Otherwise, you can have P1 and P2 and P1 sub 0 and K1 sub 0, too many indices. So what we're trying to do is, whenever we write a k, whose components are omega and little k, we know we're talking about the photon. And whenever I write a p, I know I'm talking about the electron. So omega is just an energy of the photon. So now, if I cancel all the c squares, then I get m prime square is m square plus 2 m omega over c squared. Now you can take the square root if you like, and that's the answer. So my mass would have gone up. You might think, how much would the mass have gone up? You will say, well, this guy swallowed a photon of energy omega, so maybe that energy over c squared will be the change in mass. That's not correct, and you got to think about why that's not the answer. Why is that wrong? Why doesn't the photon energy turn into my extra mass? Yes?
The final velocity changes the right factor.
In other words, when I absorb the photon, I also have to recoil to conserve the momentum of the photon. Consequently, my final energy will equal old energy plus photon energy, but that does not mean all of it is rest energy, because there's some energy of motion. So you got to make sure that in the end you calculate it so that the total energy is balanced, but it's not contained in rest mass, because you produce the rest mass and you also move the rest mass. And for all of that, you got only the energy of the photon to work with. Okay, so this is one problem. I was going to do one or two more, but I want to make sure you guys are following. I just don't know See, if I ask you what you would do next, if you have some idea, then we can proceed. But if you don't know, maybe we should slow down. And you've got to talk about which part of it you find more difficult. So let me say a few things. And the first time you hear something that you find difficult, you've got to put your hand up. Okay? Otherwise, you're not going to make progress. First thing I say is this. Particles of mass have an energy and momentum that depend on their velocity and rest mass as given by the first equation. And the energy and momentum are assembled into a 4-vector, the first component of which is E over C, second component is just the momentum. That much you should know. Secondly, if you took the dot product of that vector with itself, where the dot product is defined to be Lorentz invariant, so that it's same for all people, that's P0 squared minus P1 squared, you will always get m squared c squared for any particle of mass m, independent of its state of motion. And the simplest way to remember that is to evaluate that dot product in the frame moving with the particle. In that frame, it only has a P0, which is mc, and doesn't have a spatial momentum, so that's got to be the answer. Second thing, when you deal with photons, it's a little tricky. Photons have energy, photons have momentum, but energy is not mass times some velocity squared over 2, etc. They have no mass, but they have energy and they have momentum, and the condition of the photon is that the energy must be momentum times c. That will make sure that k dot k is 0. Because for a particle of mass m, I showed you the relation E squared equal to c times p squared plus m squared c to the 4th. For photon, there is no m. That means E equal to pc. So photons energy and photon momentum have related magnitude. Yes?
How do you define the P for a photon given that P is defined as mv?
That's what I'm telling you. For a photon, it's not defined as mv over something. It is not defined that way because you don't even get off first base because m vanishes. And v equal to 0. You're in real trouble. So you got to realize that for photon, there's an exception to how you think about it. You don't think of it as an object of some mass that moves and has some energy and some momentum. It always moves at one speed. You might say if it always moves at one speed, it must have only one unique momentum. That's not true either. So they are a little tricky. For photons, you have to accept the fact that photons have energy and photons have momentum with E equal to pc. And apart from that, there is no restriction. You can give a photon any energy you like as long as the momentum you give it is such that E squared equal to c squared p squared. So, and you cannot go to the frame in which the photon is at rest. There is no such thing. It has no rest mass. But particles with no rest mass can have energies and can have momentum. You know, when the enough photons hit you, you can feel the force. That's called radiation pressure. So they carry momentum, they carry energy. But the formula for momentum energy is not written in terms of a mass. So that's the second thing I've said. Yes?
Is the time component of the momentum and the spatial component of the momentum, are they always necessarily equal?
For the photon?
Yeah.
Yes. P0 equals, or K0 equals K1 for the photon. And if I wrote K0 as omega over C, then it means omega equal to Kc. That's the second statement. That's not obvious from anything I taught you. So that's new stuff, because suddenly I got an object with no mass, and my whole derivation for momentum started with m times some velocity and so on. So that fails for photons. But they exist and they carry energy, they carry momentum. You should think of them as particles that obey E squared equals Cp squared plus m squared c to the 4th with m equal to 0. So they obey E equals Pc. That's the second statement. Third statement is, in a collision, you add up all the p's and the k's for everybody on the left, and that's equal to sum of all the p's and the k's on the right. Can you do that? So you got to make sure you can do that part. For particles, I will tell you this particle has this rest mass, it's going at this velocity. Then it should be able to build up its energy and momentum. For photons, I won't tell you this is the velocity. Velocity is always c. For photons, I'll have to tell you this is the omega of the photon, this is the k of the photon. So you form a little vector with omega over c as the first component and k as the second one. Then it's very easy. Add all the first column, second column, third column, fourth column, and those four things are separately conserved. That's it. That's the trick to collisions. Balancing energy and momentum in one mega equation, which is 4 momentum before is 4 momentum after. And the beauty is, Any observer can look at this collision from any frame of reference. Different people will disagree on what's the energy and what's the momentum of the particle. For example, in this example I gave you, I said I am at rest and I got hit by a photon, then I'm moving. Well, that's the point of view of some observer for whom I was at rest initially. You can see the whole thing from a rocket. In that case, my initial momentum will have a spatial part because in the rocket I will be moving backwards. This photon will also have a nu omega and a nu k, which you can find from Lorentz transformation. This final object will be moving at some speed, so everything will look different. Nonetheless, the momentum and energy will balance on the two sides for you as well. Yes?
In that last condition, if a rocket is observing a collision, would you also have a different mass as well?
Pardon me?
If the collision were observed from a rocket, would there be some way to see a difference in mass as well between stationary?
No. You got to be very careful about what you mean by mass. Some people think of mass as m divided by square root of 1 minus b square root. I never want to take that point of view. The only mass is the rest mass. And nobody will disagree on what the rest mass of a particle is. Do you understand that? I may think the particle is at rest. You may think it's moving. That's just fine. But if we both ask the following question, what is its mass in a frame in which the particle is at rest? The answer to that question is a unique answer. To find that, you go sit with the particle and you find its mass. So the rest mass, in this case m and m prime, are same for all people. You can see the whole collision in the rocket, the m prime is the m prime. E and p are transforming as Lorentz variables, but m is the length square of a 4 vector, and therefore it's the same for all people. Okay, now I want to do a second very interesting problem, which is this. The year is 1950 something, forgot 53 or 54. You are trying to build a collider in Berkeley. It's going to have a proton target. By the way, I'm going to show you one more trick which is very useful. Put c equal to 1 everywhere. You can always put c equal to 1 by choice of units. For example, if your unit of length, instead of being a meter stick, was 3 times 10 to the 8 meters, and that was your new unit of length, that's called a light second. For you, the velocity of light is 1, because it goes 1 light second in 1 second, and distance over time will be 1. Even if that's not your unit, I say forget about c, do the math without c. In the end, you can always put back the c. We'll always know in the end how to put back the c. Maybe I have an example here. Yeah, in this problem, if I'd forgotten c everywhere, I'll get an answer that looks like this. M prime squared is m squared plus 2m omega. I already know that if that's the mass squared and that's the mass squared, well, that's the mass and that's an energy, so I know there should be a c squared here. You can always fudge the c squared at the end of the day. There's no reason to carry it from the beginning. Just from dimensional analysis, when you're looking for an energy, you see a mass, put a c squared there. When you're looking for a mass and you see an energy and it should be a mass, divide by c squared. So that's what I'm going to do. So here is a proton at rest. Here is a proton that I've created from my Bevatron, which is going to come and smash into this. And the job of this reaction is the following. By the way, this notation is very unfortunate. This is not a momentum. This stands for proton. Proton plus proton should form the 2 protons and a new proton and antiproton created from the vacuum, created from nowhere. This is what happens in a collider. Particles and antiparticles are created in pairs using the incoming energy. So it's the opposite of the atomic bomb. In atomic bomb, mass is destroyed and energy is created. In an accelerator, energy is converted into mass, which is why 2 particles can go in and 4 particles or 10 or 14,000 can come out. So we want to look at the experiment where people were trying to make antiprotons. The theory says the antiproton mass is the same as the proton mass. It's a very general symmetry of theories. But you want to make it. And the question is, what is the minimum energy of this incoming proton that will make this reaction possible? And this guy starts out at rest. So what energy or what momentum should the incoming projectile have? Yes?
It should have
the energy from its motion should be equivalent to the rest mass of one or two protons?
Let's see. So here are four protons. And in the cheapest collision, what will they be doing in the end?
They'll all just be like kind of
sitting in a clump.
Yeah.
And what will be the energy of that clump?
The clump will the energy will just be the energy of their respective atoms.
Do you agree that's 4m?
Yes.
Okay, this guy brings energy m to the collision, being the static target. So you will conclude the energy of this should be 3m. By that we mean mc squared divided by 1 minus v squared over c squared should be 3 times mc squared. That's the energy. Because that 3m plus this m will make 4m. Yep?
Why do we say that the proton on the right that's coming in is m, and then we define the other one is 3m?
No, no, no. The mass of these particles is always m. I'm saying the energy of this guy is 3m.
Okay.
Yes, if this is 3m, and that guy brings an m just by sitting there, and we need 4m to make 4 particles. And we want the cheapest deal, so nobody's doing anything. But this is wrong. This is an underestimate for what you need. You need more. You've got to think about why do we need more energy than this? Yep?
So in this case, the proton and the antiproton will annihilate, so they move in separate directions. So
No, let's say they don't annihilate. They form and they don't annihilate that fast. So they can be produced. Antiprotons can. That's not the reason why. I want you to visualize the question we are asking. Obviously, if you send a super duper proton beam, it can knock the hell out of this proton, produce however many particles you want. We want the minimum energy, and the picture we have is, what's the minimum energy of 4 particles? Well, it's 4 particles at rest. That's the one for which we computed the energy, but there's something wrong with that argument. Yes?
to conserve momentum, they can't be at rest.
Yes, let me repeat what he said. Law of conservation of momentum will not allow you to take a situation where a proton comes in with momentum, this guy is doing nothing, and you cannot have 4 particles at rest, because their momentum is 0. Therefore, the 4 guys who are produced must be drifting forward with some minimum momentum, so that that momentum equals incoming momentum. That means you got to pay the price to make them, you got to pay the price to move them at a minimum momentum to balance the incoming momentum. So that should tell you that the real energy of the incoming particle has got to be more than just whatever I said, 3m. So we're going to find out the real momentum. So the trick is again going to be the same. So this is the initial state, this is the final state, but this final state has got some motion. It cannot be at rest. So what's the initial momentum? Initial momentum for this guy is some energy E. For this guy is some mass m. And the momentum of this is some number p. And the momentum of this guy is 0. That's the initial momentum. And that's got to be equal to the final momentum. Very good. Final momentum you can write down in detail by taking these 4 masses, giving them some velocities, but I'm not going to do any of that. Yes?
Where did the m come from?
This m, this particle has an energy m. It's really mc. Sorry, this E over c, mc and 0. This guy has got E over c and some momentum p. I've forgotten the c. Remember, we agreed that we're not going to worry about c in this problem. So this is just m. So this is the initial momentum. That's going to be the final momentum. That also means initial momentum square is final momentum square. If 2 vectors are equal, the squares are equal. Now, the final momentum square, I say we can evaluate not in the lab frame, but in another frame called the center of mass frame. And here is the center of mass frame. Suppose you start moving to the right at some speed. What do you think will happen? Imagine in your head, you move to the right, this proton will start moving to the left, this proton will appear slower. Is that clear to you? pick up your speed until they're coming in exactly opposite momentum. That's the frame of reference you can imagine. In that frame, the collision looks rather different. In that frame, this guy and this guy are approaching each other with opposite velocities and therefore equal and opposite momenta. The total momentum is 0. In that frame, these two guys are allowed to go into four-sitting ducks because the total momentum is 0. So that is the frame of reference called the center of mass frame, in which incoming momenta add up to 0. So the final particles are allowed to be at rest if they want to, and the minimum energy collision, they will be produced at rest, because that's the least expensive way. So I found a frame in which this is possible. That's not the lab frame. That's the frame in which they're moving in opposite directions. But what's the total momentum in this frame? Total momentum in this frame, P total, is 4m, 0. Now, no one says the total momentum in that frame has to be the total momentum in my frame, but, say P final. No one says that P final should be my P final, but the square of that P final is the square of my P final, because the square of any vector is the same for all observers. So what is P final square? You guys should know by now. This dot product of this vector with itself is the square of this number minus 0. There is nothing here. Therefore, I argue here that P initial square is equal to P final square. That I calculate in the center of mass frame, and I get 16m square. Yes?
Why should the squares and momentum be equal?
Right. Why is the square of the four momentum the same in two frames of reference? Anybody answer that? Why is the momenta are not equal, but the square is equal? Why is that? Because it's a dot product of a vector with itself, and the whole idea of defining these squares is so that they are the same for all observers. The whole idea of defining four vectors is that when you take the length square of a four vector, defined in this crazy way, 0th component square minus the first component square, that's same for all people, right? That's the beauty. That's why, if you really look at the total momentum vector in the lab frame, it looks like this. And that's got to be the final total momentum too. These numbers are not, they're both non-zero. So no one says the total momentum vector is the same. In the center of mass frame, it looks like this, but the square of the vector must be the square of the vector for all people. So let me finish this and maybe we'll have a discussion. So P initial square is 16m squared. So this is the topmost line. Find the square of this vector. It's E plus m squared minus P squared is 16m squared. So let's see where to write this. Maybe I'll write it here. That means E squared plus m squared plus 2em minus p squared is 16m squared. But you must know that e squared minus p squared is an m squared. I'm saying e squared equal to p squared plus m squared if you banish all factors of c squared. So this e squared minus this p squared is an m squared. There's already an m squared here. So I get 2m squared plus 2em equal to 16m squared. You cancel the 2 and make it 14m squared. And you divide by 2m, you find e equals 7m. By the way, this is posted on the web, on the internet. So you guys can go, you guys can read it whenever you like. So don't worry about this last detail. I've given you every possible detail here. If you didn't get every factor, it doesn't matter. What I want you to understand is, I've also given you the whole argument on how you go to this frame and that frame. The point is, you get an answer E equal to 7m. Now you realize it's time to put back the velocity of light. And everybody knows, even man and woman on the street, that this should be really 7mc squared. So if you had carried factors of c throughout the calculation, it would have been very messy. But here is where c squared would have to turn up. Because if you're looking for an energy and you get a mass, you put back the c squared. So what we are told is the incoming proton, as it moves, its energy goes from mc squared to bigger and bigger numbers, because the denominator, 1 over v squared over c squared, is vanishing. Wait till the energy is 7 times the rest energy. And when it's 7 times the rest energy, that's when it's ready to hit the static proton and produce proton-antiproton pairs from nowhere. So some of the 7m squared is going to give a momentum to the fragments of the collision, and some is to create them. And the way we found out the minimum energy is we did energy momentum calculation, but the minimum energy configuration is easily imagined in the center of mass frame. That's the whole point. Not in the lab frame, center of mass frame. That's why accelerators nowadays, instead of taking one particle, make it move faster and faster and hitting a target, they produce intersecting storage rings where the particles are going in opposite directions, and every time when they meet in the racetrack, they're allowed to collide. What's the beauty of that? Beauty of that is, since they come with opposite momenta, the final fragments don't have to move at all. So you can make more and more mass. So don't put your energy all into one beam and a static target. Put them into 2 oppositely moving beams. Then all the energy is available for producing mass. All right, so I'll stop now. I think this is a difficult chapter, so you have to go and read and you have to talk to each other and try to do as many problems as